What have these three simple harmonic oscillators got to do with things moving in circles? Well, quite a lot as it happens, and surprisingly it's not that difficult. So if you feel like you need a clearer understanding of simple harmonic motion, and who doesn't, then this short video is for you. This second oscillator appears to track the pendulum. Notice that they're both at the edges of their swing or in the middle at the same time. We now replace the pendulum with the circle. As you can see, the period of the circle is the same as the time it takes the oscillator to do one oscillation. Now we add in this angle theta, and as you can see it goes back to 0 when the circle is at the top. But when the oscillator is at the bottom, theta would be 180 degrees or pi radians. When it's at the 9 o'clock position, in other words off on the left, then the angle would be pi over 2 or 90 degrees. Our next job is to try and derive an expression to tell us what the displacement of our oscillator is from the midpoint. This line shows that the two centres of the circle and the oscillator line up. R is the radius of the circle, theta the angle that it's turned, and this distance here, x, this is the displacement or the distance we are after. X will be at its maximum when the angle is either equal to 0 or 180 degrees, that's 0 or pi radians. And so at these two extreme points of the motion we can say that the radius is equal to x, or we call that the amplitude. And from Pythagoras we can also say that that distance x is equal to r cos theta. And so this means, since r is equal to a, that we end up with x equals a cosine of theta. Theta we know is going to be equal to omega t. Therefore we can substitute that in and we get our standard SHM displacement formula, x equals a cosine of omega t. We set out to answer the question, what has simple harmonic motion got to do with circles and trigonometry? Hopefully now you can begin to see and understand that connection is a close one. The oscillator on the left is moving up and down in the y direction. If we take its position at any moment and add a constantly changing x coordinate, then you can clearly see that the graph sketched out, the blue trail, is a cosine curve, therefore proving the link.